Yeah, I'm Kyle, and actually we don't work for the Valkey offering. We work for the open source office at AWS. Our entire job is to work on the open source project for Valkey. They don't let us touch any of the AWS stuff, actually, so that's probably for the best. This is Roberto.
Hello.
Roberto's going to kick in.
Hello.
He's
My
gonna
name is Roberto. Guten Tag. Danke. That's all of my German.
I wish that I had as much skill with German. I don't have any. Okay, so we're just going to go in and we're going to do a bit of a speed run when it comes to introducing you to a number of different things here. So bear with us, and Roberto's going to show you how it all kind of connects together. So this is what's on the Valkey website. I will read to you the definition of Valkey, but before I do, how many people know what Valkey is? Raise your hands. A few. How many people know what Redis is? Raise your hands. Okay. That knowledge will come in handy. So Valkey is an open source BSD high performance key value data store that supports a variety of workloads such as caching, message queues, and act as a primary database. And the project's backed by the Linux Foundation, ensuring that it will remain open source forever. So let's break this down for just one moment. Key value database, everything is related to a key. It has a type, a structure, and a series of commands that you can use to access the data. It's a Linux Foundation project that is open source forever. So Valkey is the fork of Redis. So a couple of years ago now, Redis had a license change. Half the maintainers went to form Valkey. So that's where we come from. So a lot of these things, if you know Redis, it's going to be very familiar. There's a few differences, but it has diverged in the intervening time. So high performance, about 1 million operations per second on a single box. If we want to go to the largest cluster we know is possible, 2,000 nodes will give you about 1 billion operations per second. No one in the world needs that, so don't even try it. It's silly, but you can do it for some reason. It's primarily used for caching because it's an in-memory first byte addressable database. And then usually I go into talking about how it's a messaging queue, but this whole thing's about messaging queues, and you know what messaging queues are. So let's just talk a little bit about in-memory messaging. So why in-memory, right? In-memory is low latency and high throughput. It's how we do everything, really, when it comes to writing anything in a application in any way. So that makes sense if you want to go high performance. And messaging is kind of a balanced read-write workload. And what's great about in-memory stuff is that we read and write it at approximately the same speed. So it kind of matches that. And it's pretty easy to scale things that are in memory kind of natively. What it means is that we really have less to worry about. We don't have any disks that we talk about. There is a way to persist to disk, but it's not part of the scaling of it. So you can scale out to thousands of nodes without losing hair in the process. So what people know most about Valkey when it comes to messaging is fire and forget, pubs up. So let's look at how that works. Now, many of you have flown here. I flew here, so we're using a whole series of like airline examples in this demo or this presentation. So here we have a number of applications. They are subscribed to a number of channels. So you can see these flights, FRA, whatever. And then what happens is another application will publish to that channel. Those are called channels. They'll have a payload, and then those payloads, when they publish it, will be delivered instantly to the different subscribers. And so you can see here, that's one. You can also deliver to multiple subscribers as well. What kind of people forget about this? We go and say it's fire and forget, and people don't understand that because they try to do things. And they try to say, well, what happens when an application is offline? Well, nothing. It goes nowhere. It's gone. Roberto talks about the fact that it's kind of like having the radio on and going through a tunnel. When you're in the tunnel, you don't hear the radio, and there's no way to retrieve that when you exit the tunnel, right? It's fire and forget. It has its uses, but it's not really useful for directly messaging. It's usually as a component of something else. Now, where Valkey is used more is when you start using some of our other data types, such as lists, and that's used to build queues. Lists are just doubly linked lists that you probably learned about in ComSci 101. In this case, we're using a command called lpush. We are pushing into a key called flights, and we have two items. We're pushing to the left side. Each one goes to the left, so it would look something like this. So our first argument is LH444, so it goes to the left side of the existing elements. And then we have EW112 that goes again to the left side of that. And then we can pop items off the left side. And that's, in this example, if we have this, we're going to get the item that's directly off of that, and we have that value. So not that complicated. We can also do it from the right side. This is the same exact set of commands, but we're doing to the right side instead of the left side. So everybody with me? Everybody should be good here. Then we're going to start talking about how we can use these in actually a useful way. So when we start looking at this, you can start. We're going to see we're going to use this concept called blocking in Valkey. Basically, that is a way to prevent you from having to pull something. It will wait for something if it doesn't exist. So we are doing a left side pop from the key flights. We're going to have a timeout of 1,000. If that doesn't exist, then we're going to actually retrieve. We're going to wait for 1,000 seconds. In the intervening time, we L push into something. It will be instantly delivered to the flight, the blocking item here. So keep that in the back of your mind. All the existing, or all the rest of the commands that I'll talk about in the presentation have the same idea to block, or it will be used in some way. So moving forward, when we're doing this, we can also L push a number of items in, and we're going to build a queue with this. So right now we have some data, and it represents what you see here. And so it has 3 items in that list, plus any additional items. We have this thing where we can move between lists atomically. And so in this case, what's happening is we are moving from the left side of flights to the right side of a new key called process flights. So what we have now, it'll return the item that we moved, but it will also have 2 different keys. And this is what it looks like now. So we have where we are in this situation. We removed EW112, and it's now in a new key. So as we move on, we can then do some processing on that returned value, whatever that might be. It could be something like, sending it to an API. It could be doing some sort of calculation on it, whatever that takes time. When we're done with it, we can then remove it from the processing queue, and we are safe. Everything has happened here. What's really good about this is that we can have, you see we removed it from that processing queue. We can have any type of failure here that we need. Because we have moved it atomically around inside the key value store, nothing has happened, right? We can go and process that again if it fails to process it and remove it at the end of the processing system. So this is good and this is useful. People have built entire queues based on this in their applications, and we see a lot of people using this. But we have other features as well. One of the things that we see people using is sorted sets, which is another one of our data types that we use for priority queues. Sorted sets are an interesting concept for those who haven't been introduced to it. It's a set with a series of members that has no repeats in those members. Each one can have a score, and the score has a numeric value, and scores can be repeated. So how this looks is, in this example, we have member foo and bar, and they both have the score of 1,000. That's OK. But we can't have foo to have 2 different scores. That's not allowed, because a set, when you try to change the score, will basically do like an upsert to that value. So let's see how we can make a priority queue out of this. So in this case, we're doing a very simple priority queue. The more requests that we have, each time it will kind of increase the priority of that item. So in this case, what we're going to do, we're going to use the command z increby, which means Z is how we denote all sorted set commands, into the key flights. And we're going to increment it by 1, and our payload is EW112. So in this case, this is what the data looks like at this point. It wasn't there. It created it if it wasn't there. So we just assumed in this case that flights is an empty key. So here, we're going to do a Z increby for an additional flight, LH444. And so now we have 2 members in our set, and they each have the score of 1. And then we have another app that will go in and do an increment to EW112. And so now we have moved it up in the priority queue. So we can see how we could do this over and over and over again. What we can do here is we can start by saying how we're going to process that. We have a command called zrev range. So basically get a descending order by score. From the 0th element to the 0th element, so those additional arguments on there will tell you what it is. It's going to return that value. And You can then do additional processing here. What most people do will then add it to a processing list, as we showed in the previous example. And then we would remove it. Now, the problem here that you see is that it's not atomic right now. Valkey has a built-in Lua transaction engine that will allow us to run these things transactionally. So if there's any failure, it would actually not add it to the processing queue. It would fail all or nothing. So that allows us to then go back and look at it from again if we have a problem. So this is where we go for a long time. People have built entire queues off of this, and there's applications that Roberto's going to show. But we have even another thing that you can use for messaging, which is our streams. I saw some of the presentations earlier. This is going to look very familiar to a lot of people. It's basically the stream data model where each key contains a series of entries. Each entry has a unique ID that is based on a millisecond precision timestamp and an incrementing number from there that creates a sequence. So if multiple items come in the same millisecond, they get a unique ID. And each entry has a series of fields and values, which are the payload. You can read these entries by range from one or more stream keys. So you can actually read multiple streams at a time. And then you manage the processing and acknowledgement of that through a consumer group. Now, we've said the K word several times. If you know Kafka, these are all very familiar concepts to what's going on here. So let's look how you would build something with this using Valkey. In this case, we have added 3 things. All of the stream commands start with an X. So X add, and we're going to add 3 different items to that, what will become our queue here. And they're each going to have these IDs. So they came in at the same millisecond. They each get these incrementing sequence numbers. Then we're going to read from those streams, and we're basically saying, hey, give me 2 values, count 2, from streams, flights, starting from 0, which is the beginning of time. And it would return this value. Your application would do some sort of representation to whatever it looked like. This is how it looks in our CLI, but it would probably come out as a series of dicts or whatever in Python. So that's how it looks now. This is useful, but we can go further because we actually haven't talked about how we're going to acknowledge and process those items. So we have the concept of groups. We're going to create a few groups here. Those groups, we have one for meals and cleaning, using this idea that maybe you need to stock a flight or whatever. Here we're going to read from a group. In this case, we're going to read from the group meals, and every time a reader is there, it has an identifier that they use. In this case, I'm just using my name, Kyle. It would not be a person's name in a typical fashion. So when we get this, we're going to return the value out, and that's going to return the first one that we added in, because we haven't read from that one before. And then we can read from a different group, and we'll be able to return those values back out again. And so we're getting the same values because they're reading from 2 different groups. So group cleaning and group meals, that's keeping track of where they are. And from here, we can then look at the pending list. So we're going to look for the pending list. This is going to tell us what we haven't processed yet for a specific reader and the group that it's in. And that's going to say, hey, this one that we looked at for meals, Kyle has not processed this one. And we have a timeout value in it. That's the 65,000 bit at the bottom here. So what we can do from here is we can actually go in and start thinking about how we are going to acknowledge or reclaim those values. So in this case, we have the values that we had before. We are going to do X claim. I wish it was called X reclaim because it's really about reclaiming data. So we're going to transfer that from Kyle to Joe, and there's a timeout value on this too, so it would only claim it if it exceeds a particular timeout, and then we would get the value back out of it with its new owner. So Joe owns that item, and then when we're done with it, we can acknowledge that item, and when we do the pending again, it'll be an empty array. So there's nothing there. And if we were to look at this again, with our reading our group again, basically we're going to see the same values back out of this, where we've had this. And if you notice, the EW112, which was our first one, is now gone because it's been processed, and it's not anything that we can read any longer, although you could read it without a group and still see it in the actual data structure. Now, I have thrown a lot at you all at once. This is like a speed run. This is what I'd usually do in about an hour, but I know people know messaging in this room. But to put it all together, I'm going to bring Roberto up here. He's going to show you how it's actually done with a common package.
Thank you. And I know it's just me between you and lunch, so I'm going to try to make this quick. And like Kyle said, we probably all came. I'm going backwards?
You're going backwards.
Yeah, I'm sorry about that. We all came probably some way on train or flights. If you had the luck, like I did, to be a passenger on a given flight, right? It was, in this case, we have two characters, Jane and Joan, and something happens. And it happens very often, especially in the US, where you get delayed and then you need to send a bunch of different notifications, right? And this causes people to go like this, right? So essentially, we're like, oh my gosh, like, I have to go do something. And like Kyle mentioned, there are a few things that we can use, like pretty much to put all the different data structures and things together. There are several libraries such as Celery for Python, BullMQ for JavaScript, Scikit for Ruby, and even for Kubernetes deployments, something called Kata for autoscaling. So you using Valkey as one of the data stores that helps you scale. How do we do this? In this case, we're using Valkey as a broker and a backend. And we have a producer, which is our Celery application, and there's an event. So in this case, flight gets delayed, and we're using that list data structure to push into a queue called Celery, and we pass all the data about the task. And then we also added to a sorted set, as well as a hash to keep which are the unacknowledged tasks. With the sorted set, we have the ability to now have a priority queue. So let's say there are some things that get delayed and they don't get processed, so we can go in from the untracked index, make sure that, yeah, the first came in, they're also the first to go out and get processed. And we have a worker reading from that queue. In this case, we pop the elements from the Celery task or the queue, and then we're going to get a meta or a meta task with 3 different tasks. Remember, we're doing SMS, push notifications, as well as an email. And then we go and remove it from the unact queue, as well as the hash, where we're keeping track of the values. And then once we're done processing, we store the results on the backend, in this case also using Valkey. And we publish a message. Remember, that's just a broadcast. So it's a channel where we say, okay, we're done with this task. This is the result. So the worker, I'm sorry, in the case the producer, can read from that channel and get like, okay, I have the results of this given task. So I'm going to go to the console and run some commands for you. Oh, I'm sorry, I'm going to have to unplug and plug again. Sorry about that. Oh, no, it did not work. I had to make a single screen so I can see what I'm doing here. So mirror, and that should work. Can you see this font size correctly, or should I go a little bit closer? Is it good? Thank you. Perfect. Excellent. So let's run our demo. Let's first clean up our databases. Perfect. And then if we go and start the demo, this is a Python project, right? So it's super simple. We're using in this case, 2 different servers. We have Valkey 9 over here as our Valkey core. And then we're also using the Redis open source version 7.2.4 on which Valkey was forked. And we can go and see on this second tab over here in both running. So we have Valkey as well as Redis, right? So this proves the compatibility that both of these can have. So essentially, Valkey is a drop-in replacement for most of the applications that currently use Redis open source. So like I said, it's a fairly simple Python project. These are some of the packages that we're using. We're using the Celery library, Pedantic, just to keep track of the models that we have. And in this case, we're using Redis and Valkey as well. Okay, so we synced our packages, we have a couple models, the passenger, which has a few items about the person, and the flights, which has the airline, departure, and arrival airport, as well as the status, which can be on time, delayed, canceled, or boarding. And we're going to take a look at our configuration. So first, what we're doing here is telling Celery that we're going to use both as a broker and a backend, in this case, Valkey and Redis, or it could be both Valkey. And we're going to use JSON for most of this. And then we have the three different tasks, in this case, sending an email, which we are simulating just by doing a sleep of 2 seconds. And then, of course, you can use an API to actually deliver the emails. And then sending an SMS, this could take a little bit longer depending on the carrier, right? So we're simulating about 3 seconds. And finally, we're doing the push notification, which is a little bit faster, just to demonstrate how these tasks will operate asynchronously or non-blocking, for what I learned from the keynote. And then finally, the main task, which will process the flight status updates, where we'll take a flight and in this case, we're mocking the passengers, Jane and Joe, that we saw earlier. And but of course, it could be coming from a database, or it could come as the payload of the function call as well. So all we're doing is, for all those passengers, we're going to go and send these 3 different notifications. Okay, so that's good. And then this is our main program, where we have 2 functions. One is the flight delay, that is giving us that you are going to be delayed from Paris to Berlin, like happened to me. And then boarding, when you're going out, for example, from Berlin to Marseille. And we are doing also just a quick 1 second pause just to see things on the screen. And once we have that, we are able to process our worker. In this case, we do see that Celery is using both the backends for using the Redis connector, right? In this case, 2 Valkey and Redis open source. So I'm gonna log into here in the same folder. Okay. Good, GitHub, perfect. That's where I want to be. And let's do the demo. Step 2. If you recall, what I'm doing here is I run the monitor command on Redis as well as Valkey. In this case, Valkey is a broker. And as you can see, Celery is already like doing some status updates, for example, doing a heartbeat, as well as verifying if there are any items on the queue. I need to spell my demo properly. There you go. So in this case, we do not have any tasks currently running, but if I press the next command, that's going to do and process those 2 notifications that we saw. And they're going super fast, right? So in this case, I was able to wait for 1 second and then get the payload of the active tasks that are happening. Above, we see the worker, and we can see the different messages that were sent. So all the notifications going for the flight GA that has been, in this case, delayed. And we can see that the push task for John did not happen because he does not have a token. But that completely, really quickly, right? We didn't even have to wait for the 1.1 and 1.5 seconds, whereas for Jane, we did wait. It took 1.5, but that's, even though it was the last message that we sent, or the task that we sent, it was the first to get processed, right? That's where the asynchronicity or parallel processing happens. And all of this, as you can see, we didn't have to write any Valkey specific code. It was just Celery doing the work, and all happened over here behind the scenes. We can see a bunch of the all push commands, and then we can also see the PR pop. Remember, Cal talked about how we're blocking until there is something on the elements on the queue. And then we can also see over here on the storage or the backend, I can go and scan some of the tasks that happen over here. This is the results of a task. And I can go and get the payload. And there is something else that we didn't discuss with you that I would like you to learn, which is very, very important in the in-memory world, where you can have a time to live on every key that you set. So in this case, I have a key, and it's called key, and I have a value called value, right? But I can very well have a key called country, and then the value is Germany. All right, so I can go and say, get me the key or get me the country. So, okay, that's fine. That's very good. But what if I want to see for how long the data is going to store or going to stay in memory? So if I want to see the TTL on the key, it's -1. That means it's always going to be there in memory until the server gets rebooted, right? So if you want to say, I want to expire the key in 5 seconds, if I run the TTL again, I'm going to see how this value is getting decremented, and eventually that key will no longer be available. So whenever I want to do the get, right? So that means I don't have a value, and this -2, that means that it did have a time to live, but now it has been lapsed. So if we go to the get task, right, I can also get this key and see the TTL on it. That means that this is about close to 24 hours, right, over 23 hours. So the idea is that we're showcasing here how Valkey can be used as an extremely low latency and reliable system for messaging, using all these different structures that we talked to you about today. And we will love you to contribute. There are a lot of things that we can do to enhance, for example, the use of streams. And in this case, we will like you to get involved. Go to the Valkey.io website, download and test it out, and yeah, contribute if you can. Thank you so much. I think we're good to go. Yeah.